Okay, in this video I'm going to show you how to build your model in Coot. So we've already centered on the last residue in our sequence, and this is glycine 520. Now if we click on the last carbon here, and this is the carbonyl oxygen at the end, we'll notice that our blue mesh showing us our electron density continues on from this point, but we haven't got a model, and this is because I've deleted the model so that you can build it in. Now if we were really building this model from scratch, we would also see big green blobs as well as the blue blobs here, because when we calculated the map we didn't have the phases for this area. But as I've just deleted them, we just have the blue, but we can build into that, and that's fine. So first of all, we need to start by adding a new amino acid to the chain, and we can look down our list of commands here, and we can find add terminal residue. If we click this, for the first time we do anything that Coot tries to build into the map for, it will always ask us which map we want to build into, and this is very important, especially if you have more than one map open, to pick the right one. So if you remember from previously, we have two maps. We have our FWT, which is our blue mesh, and our del FWT, which is our green and red blobs. And if we had other maps, say for the 3 angstrom structure here, it would also give us those choices. So make sure that you pick the one that you want to use for the model that you've got displayed. In this case, all we've got is the 2 angstrom map and model, so this is the correct one. We can click OK. If we're ever not sure what map Coot is looking at or using, we can also click on this button here where it says select map, and it will bring up this same box. So we've selected this blue map that we're looking at. So because that time it took us to the map, we need to then click our button again, add terminal residue. And then what we do is we click an atom close to where we want to add it to. And what Coot does is it looks at the map that we've selected, and it tries to place this residue in a sensible place within the map. And we can see that it initially puts it as white sticks until we've clicked accept. And because this looks vaguely in the map, it's good just to click accept, because we can always move it at a later stage if we want to. So if we turn it around a bit, you can actually see that it's added on quite well. It's just an alanine that it's done with 1 carbon in the side chain, but that this carbonyl oxygen fits nicely into the bump into the map. And we can click with the wheel, and we can center on this new residue. Now obviously, well hopefully obviously to you, you can see that this residue is not an alanine because it's got all this extra side chain density here. And because we know our sequence, but you might be able to tell anyway, you know that this residue is actually a tyrosine. And if we look at it, you can actually see it's got a sort of circular bump, but it's also got a bit that sticks out at the end. It's not totally circular at the end. So we need to change this residue to a tyrosine, and we can do that in 2 ways. First of all, we could click on mutate and auto fit, and then we click on the residue we want to mutate, and it brings up a list of amino acids to choose from. So tyrosine is here, Y. And what Coot has done for us is it's not only mutated this to a tyrosine, but it's automatically fitted it to the density, and that looks pretty good to me. But it doesn't always do this correctly, so I just want to show you the other way as well. And this we can click undo, so whatever you've done you can always click undo if you don't like it. What I've forgotten is what it does first is the auto fit. If I click undo again, it's gone entirely. So we can also use the simple mutate button, and this, once we've picked our tyrosine, just mutates the residue to tyrosine, but it doesn't automatically fit it to the density as we saw a minute ago. In this case, we can then fit it to the density ourselves, and there are several ways of doing this. One of these is to click auto fit rotamer and click on the tyrosine, and it's put it back where it was before. So this is doing the auto fitting in a separate step that we did originally with the mutate and auto fit. Click undo. Just to show, we can also click rotamers, and in this case it brings up a little box with the most likely positions for this side chain. So if we were going to do it this way, we'd probably decide that this one was the best and click OK. But this isn't actually that well fitted, and the reason for this is probably because the backbone isn't totally as well fitted as it could be either. So the final thing I want to show you is called Real Space Refine Zone, and this will refine sidechain positions or the backbone, and you click two atoms and it will refine between those two atoms. Now in this case I just click the same atom twice because I'm just interested in refining this amino acid by itself. And again, if you see, what it's done is it's created for us a new model in the white sticks that we can either accept or not accept. Now this again looks like the nicely fitted one we had earlier, and it's clearly better in the density than the green one. And what I accidentally just showed you there, that actually if it doesn't do this well, you can actually, in this state, if you left click an atom and you drag it, you can actually move it into a new bit of density like that. Now clearly that's not where this wants to go, but in a situation where you may have more trouble fitting something, that's the way to do it. So that's quite cool, that's the fun bit. After it's put it in, it brings up this box and it tells you whether the bond angles are what we would expect for these particular bonds. And you can see that green, you might be able to guess, means good, and yellow means less good, and if it's red, like we saw when we moved it into this part of the density here, that means bad. But we can straighten up these bond angles a bit more if we want in a minute. So we'll click accept there because this new confirmation is a lot better than the previous one. And if we want to just tidy up those bond angles a bit more, we can try the regularized zone. And again, this takes, you click twice, so just for this residue we can click twice on the same atom, and what it's done is it's just straightened it out a bit. So this does the same as the Real Space Refine Zone. It tries to provide a confirmation with good bond angles, but it doesn't try to fit it to the map, it just straightens out the bond angles. But if once we've straightened them, it still looks like it fits nicely in the map, because we're trying to achieve good bond angles and fitting the map, we can click accept, and we'll be very happy with this confirmation. So we could have done that very quickly, but I just wanted to show you the different options for building your sidechain into the molecule. We then just go on to have a look at the next residue as well. We can add terminal residue again. It doesn't ask us about the map this time because it already knows which map we're using, and if we wanted to change that, we would click the map button. And again we get the little crosshairs, so we click on an atom near where we want to build the residue for, and it's placed one in the density at a suitable distance, so we click accept. Now this one you might think doesn't fit quite so well, the carbonyl oxygen's in this little bump here, but this carbon's sort of pointing out of the density, and we can see that the side chain goes this way, although the density isn't very good for this side chain, and this red blob suggests that maybe there was some disorder in it that we weren't able to model when we did the refinement. But we can center click with the mouse wheel button to center on this, and then we can mutate it. So let's try the mutate and auto fit. Now we know from our sequence that this is a glutamate, so we find glutamate E in our list and let it do the auto fit. Now this doesn't look particularly well fitted, does it? Because you can see this little carbon is stuck out of the density here, although the carbonyl oxygen is nice. We could try using the Real Space Refine Zone here, and it's moved it, and that looks a bit better because it's sort of straightened it out a bit, and it's filling more of this density up here. Oops, no, I don't want to do that. So that's probably quite good, and as we can see, all of our bond angles are green down here. We'll click accept, and that looks okay. So with a good map like this, you can actually do this quite quickly. So we can add another residue, add terminal residue, click accept. Now this looks very strange if you look here, because the carbon of the sidechain is pointing completely out of the density, which doesn't look particularly good. But if we go back to our sequence, what we'll see is that this residue is actually a glycine, and so we can either use mutate and autofit or simple mutate. It doesn't really matter. If we click glycine, glycine doesn't have a sidechain other than a hydrogen, and so it's just got rid of that carbon that's sticking out. So this is okay. It's not particularly well modelled, but glycines are actually quite hard to model in the density by themselves. It's good to have a stretch. So we'll just put this last one in here, and then we can see if we can get a better position for the glycine. So finally, add terminal residue, click on our atom, and it's put a new one in. Now again, this density looks a bit strange because it's got a whole big blob over here, and the side chain looks to be pointing this way, but there's nothing going up there, although the carbonyl oxygen around here at the bottom is nicely in a little bump. But if we look at our sequence, we'll see that this is actually a proline, which explains why the density looks square like this. So if we mutate and autofit this proline is P, you can see the side chain goes back to the nitrogen, and it fits quite nicely. And now what we can do, now we've built several residues, is do this real space refine zone over 3 residues. So I clicked here and I clicked here. What this has done is it's just adjusted the proline within its blob here and moved the glycine back more into the centre of this bit of density here, and it's kept this aspartate side chain in the same position. So we were happy with that position, but this doing it over 3 residues has just allowed us to get a nicer position for the backbone along this stretch. So obviously there are a few more residues to build, but I don't want to ruin all the fun for you. The important thing to remember though is that if you've done something that you think would be worth saving, it just in case computer crashes, is to save coordinates. So this is the one here, save coordinates, and what it offers you is a list of molecules. So if you've just got one molecule loaded in your 2 angstrom model, that's fine, this is the correct one. If you had more than one molecule, say you loaded in your 3 angstrom, you would have to check that you've picked the right one out of the list. The easiest thing to do is only to have one at a time. So this is the thing we've been editing, and so once we've picked the right one, we then click select file name, and we can choose a new file name for it. So coot0 is not very helpful. You could call it something like edit1 or residue1, and then just click save. And do check where you saved it to, so you can go back and find it.